Let's begin our session. The first one, I guess, we mostly expected the keynote speech given by Dr. Joachim Schellnhuber. I'll give us brief introduction. I guess most of you already knew him very well. Yesterday I went together with Dr. Schellnhuber to Yale. And, my purpose is to get know him better, then I can do better introduction today. Okay, actually, he's a physicist. Okay, this is a very special physicist. Usually stay with the computer if you're a theoretical physicist. If you're experimental physicist, you'll stay in the lab. But Dr. Schellnhuber liked the nature. Yeah, I guess the reason because he grew up in mountains Alps, so he likes nature. And he got too many prize and medal, so I don't need to read and know. Some of them are important, like he's a member of Pontifical Academy of Science, German National Academy, Leopoldina, U.S. National Academy of Science, and Academia Europaea. Those are important academic honor. And, he actually worked with a lot of scientists to lead the IPCC report for many years. So in 2007, just mentioned, awarded by Nobel Prize. Well, today, I guess the people would like to learn more the recent progress, what's going on internationally about the climate change and the climate challenges. So he is going to give us a talk entitled The Climate Challenge and the Great Transformation. Please, Dr. Schellnhuber.
Yeah, good morning, everybody. Thank you very much for the nice introduction. Actually, we went to the Geopark yesterday to look at this famous Queen sculpture, and I was very impressed. And it's true, I mean, I'm a theoretical physicist by training and mathematician, but I do love nature. And in the end, we always need to appreciate what is at stake currently, globally. Let me also make a remark in the beginning on the situation and challenges and the responsibility Taiwan is facing, because it is a small island and you have no energy resources yourself. There has been coal mines, they have been abundant because on the global market you get it much cheaper now, so imported probably Australia, Indonesia, other places. But you have a very, very good sort of science and technology community here, which is important. So I think Taiwan can, when it comes to innovation, even disruptive innovation, so I had a very good discussion yesterday with Dr. James Liao, the current president of the Academy, on how to use natural solutions, so to speak, to enhance photosynthesis, things like that. So there are many ideas which can be developed here in Taiwan with international collaboration and can be presented to the world in order to overcome the climate crisis. Well, you have other countries like, say, Australia, they have all the natural preconditions in order to develop green energy, so we could become the biggest source of power to gas, that means hydrogen derived from solar and wind and could be export it actually to Taiwan instead of liquid natural gas, which in the end is no solution to the climate problem. It's just an intermediate step. So hydrogen would be definitely part of the final solution portfolio. But we do very little in climate innovation, for example. So in the end, it's a global division of labor, really, where every country can play an important role. So Taiwan should be part of disruptive innovation when it comes. But of course, you also need to advance your own deep decarbonization plans. But I fully appreciate that the boundary conditions are difficult. So Australia, in principle, is in a much better situation, but they do very little. So when it comes to innovation, I think Taiwan is really important. So I was here in this very room a few years ago. In the meantime, a lot of things have happened regarding climate science. So the state of the art has been advanced dramatically, really. On the one hand, so I'll tell you about it, but also we have now in place in Germany new climate policies. European Union has made climate action the main focus of the next period. So a person whom I know very well, Ursula von der Leyen, has just been elected president of the new European Commission, and the next research program, worth at least 100 billion euro, will be mainly dedicated to climate and energy issues. So this is really a statement that science and technology is absolutely needed to get us out of this crisis. So each academy in the world has to contribute to that. So let me walk you through the current situation we are facing. And it has been mentioned that already in 1993 I started to think about the 2 degrees limit of global warming. And of course, in the meantime, people have set an even more ambitious target, 1.5 degrees. And I will show you why this makes sense. On the other hand, we have lost 30 years in the meantime. So it is the typical thing politicians do, and we did it also in Paris. If you feel that you cannot reach an ambitious target because you have no practical action in place, you set an even more ambitious target, which is, in a way, an illusion. So if in the end the world would be able to limit global warming to 2 degrees, I would be more than happy, actually, because we could avoid some of the worst impacts. 1.5 degrees is probably pie in the sky, but it's nevertheless good to be very ambitious in order to achieve at least the other target. So let me start, and just to remind you, I mean, everybody knows that, but there are still people, I don't think here in Taiwan, but you have them in particular in the United States of America, who still doubt that global warming exists at all. So if this would be the stock market index, for example, would you see a trend here? Probably yes. So clearly you have an upward trend. Of course, this is global mean temperature, and you know it goes up and down, you have fluctuations. But clearly since 1970, you see a tremendous trend, and we are now at more than 1 degree global warming, and seeing already all types of impacts. And you see, this was, of course, a super El Nino here, but it's climbing up again. And this year probably is on course to be the second warmest on record, which is amazing because we have El Nino neutral conditions right now. So with the next super El Nino, which is due to come in the next 3-4 years and so on, this curve will even go up further. So we are on course towards 2 degrees now. So now what people experience in their daily life is not climate, but it is weather, so extreme weather events. And of course, Taiwan is an island where you are used to all types of extreme expressions of nature, be it earthquakes, volcano eruptions, and There is a volcano nearby, I was told, where you just try to find out whether there is a magma chamber, where is still, when it could be really a threat to Taipei. You will know in 1 year from now, I learned. But you have typhoons, and clearly the strength of the tropical storms has been increasing. The Bahamas just have been struck by the strongest hurricane on record, really, and the northern part of the Bahamas have been completely destroyed, and it would take at least 30 years to reconstruct the communities there. But we have experienced that as well in Europe. In Europe, you still think you are in a safe haven when it comes to global warming, no hurricanes and so on. But we had tremendous heat waves, so Europe heat wave was finally moving to Greenland. So you see, shatters several records we had in Belgium, Luxembourg, Germany, Netherlands, also in England. So the highest temperatures ever recorded this summer here. So Paris had 42.6 degrees, but it's probably a temperature never reached in Taiwan so far. And the same happened in Germany. So here you see the picture. It's really amazing. That was a heat wave where hot air directly came from the Sahara Desert and moved into Europe. And you see, I mean, 45 degrees in Spain, 45 degrees in southern France. When later on it crept to 42.6 degrees in Germany and so on, reaching up to Scandinavia. And this has really woken up the public. So we had last year already a major drought in Germany, but this was unprecedented. And so people finally feel, oh, it's real. It's not just professors for theoretical physics are doing calculations on the back of an envelope and say, oh, the world will perish in a few years from now. No, it is what you feel. Because at 40 degrees or 42 degrees, I mean, it's no fun anymore to go outside to have a barbecue or things like that. So the public is now aware of the climate crisis also in Europe. And then, of course, if you look around the world, that is really disturbing. You see that forests are burning in the Arctic. I mean, lots of discussions have been done about the Amazon rainforest. I will refer to that. But actually, even bigger fires have been raging in the Arctic, in Siberia, for example. Millions of hectares have been burning in Alaska and so on. And this has a very interesting effect, actually, because, and I will refer to that a little bit later, through a complicated series of processes with heat waves and the wildfires in the Arctic accelerate the thawing of the permafrost. And you know, if the permafrost is thawing, then a lot of methane in particular, but also CO2 is released, and this is accelerating global warming. These are the famous and dangerous positive feedback loops which will be set into operation. Now it has to do with a field of research. I also presented it a few years ago, but now it has developed into a very active field of research. This is about the so-called jet stream. You know, this is the ribbon of high-speed wind above 10 to 12 kilometers above the ground. And here you see a so-called Rossby wave, because the jet stream is driven by the difference between the temperature difference between the Arctic air, which is very cool, and the moderate air in our latitudes down to the subtropics, actually. And often it is forming these big bulges, so that's a Rossby wave going from the south to the north, and you see hot air is coming from Mexico all the way up to Alaska. So this is a situation where you have a heat wave over the Midwest of the United States. But in general, this wave just moves away within 2 or 3 days to the east. and finally it will arrive in Europe, and it's almost like a quantum wave, because such a wave, it may have 7 troughs and 7 crests, and it has to go all the way around the planet, so it is a planetary wave, actually. Now, the interesting thing is that these waves tend to get stuck, stalled for more than 2 days or 3 days. They become stationary, and they can last for 6 weeks. Or last year in Europe, this Rossby wave over Central Europe stayed there for 8 months, actually. And that is, of course, the precondition for drought and heat wave and everything. And this was an unexpected effect of global warming. So we, around 2000, looking at the wave equations, looking at the satellite data, were proposing this to happen. Why? Because the Arctic is warming much faster than the rest of the planet. That means the temperature difference that is driving the jet stream is becoming smaller. At the same time, the oceans are warming much slower than the continents, because they have a different heat capacity. That means along the rims of the continents, these waves get stuck. So both vertically and horizontally, we have a reorganization of the atmosphere. So it is the dynamical pattern which is the result of global warming. And so global warming does not just mean thermodynamically it gets warmer everywhere and you have more evaporation. No, the circulation pattern in the atmosphere is reorganizing. That's very important. And this was unexpected, actually. So we discovered that effect some 15 years ago and thought, we were very excited about it and thought, now this is a really interesting and subtle effect of global warming, and tried to publish it. And you know, when you publish, we are here at the Academia Sinica, you first submit to Nature, and if Nature declines the paper, then you go to Science, and then you go down all the way to the 3rd tier, Climate Dynamics or whatever. And this paper was rejected everywhere. So I knew we were up to something really important. It's always like that. If you argue against the mainstream, you have a very hard time. Now, since I'm a member of the National Academy of Sciences, I'm entitled to contribute papers, where you are still reviewed, of course, but you have a better chance to get it published. So finally, we got it published in 2013, and now it has developed into an entire field of research. So this is, for example, a paper written by Michael Mann in Scientific American. Once you publish once a topic is picked up by Scientific American, when it is popular, so when it is really mainstream. So he was heavily referring to that. And here you see what is happening. You have this jet stream forming these bulges here. You have low pressure and high pressure system. And for example, in 2018, you had this big Rossby wave stuck, actually stalled. And you had, for example, over Europe, this huge heat wave, which was even setting the forests in Scandinavia on fire. And on the back of it here, for example, you had a southward facing Rossby wave, and you had extremely cool weather over the eastern part of the United States. And who would have expected that global warming is creating patterns like this? So this is really physics, and you see how exciting physics can be. But the effect is that we are facing extreme weather events of a completely new quality now. And it's an intermediate effect, because finally the Arctic warming will sort of slow down, and the warming of the temperate regions will catch up. But for the next 50 years or something, we are expecting more weather events like that. So you see that science can see things politicians cannot see, because you need to understand, for example, the wave equations. So this is part of, it was said by Sabrina before, so I introduced this map of what is going to happen with global warming? Because so far people always thought, yes, as I said, it's getting warmer, you have more precipitation because you have more evaporation from the oceans. But these are the elements in the climate system that are really at stake. So you can call them the vital organs of the planet. So for example, you have the big ice sheets here, Greenland, West Antarctic, East Antarctic. You have the big ecosystems, the Amazon rainforest, the Great Barrier Reef, and you have the big circulation patterns, the Indian summer monsoon, very important, but also the West African. You have the thermaline circulation, the Gulf Stream system, and you have the jet stream here. And the really important question is, are there tipping points? Are there critical thresholds? So with warming of, say, 2 degrees, will the Greenland ice sheet melt down? And once it starts to melt, it's an irreversible process. Why? Because if you see the ice sheet is about 2,000 meters thick in some parts, so it's high up in the air. So if it starts surface melting, when the top layer is molten down, when the surface is moving towards warmer air, of course, and it becomes rougher, so it reflects less sunshine. And once you do not have enough snow to compensate for that, it will sink into deeper and deeper latitudes, altitudes actually, and the melting cannot be stopped anymore. And the question is, when will it happen? At 1.5 degrees? Now the best estimate with irreversible meltdown will start at the 1.6 degrees or at 2 degrees if we are lucky. So you see what global warming will do. It will activate a number of switches in the planetary machinery. And we need to know where the switches are. So I give you, this is the example on the Greenland ice sheet. Thermaline circulation, which is providing a lot of heat actually transported to Western Europe. A colleague of mine, or colleagues of mine, have just published a paper showing that over the last 50 years, this Gulf Stream system has been weakened by 15% already. And the odds are, by the end of the century, it's more or less a 50-50 chance that the Gulf Stream system is stopped down completely, shut down completely. As it happened in the past, the so-called Heinrich events, well documented. So this could happen, and that would completely reorganize the circulation patterns in the Atlantic, for example. And then, of course, there's a lot of speculation whether the Amazon rainforest is approaching a tipping point. So my colleagues Tom Lovejoy and Carlos Nobre from INPE in Brazil, we published this paper, more or less a year ago. Is there an Amazon tipping point? And the idea is the following. I mean, you have global warming, which is putting a lot of stress on tropical rainforests. But at the same time, on the ground, you have logging, slash and burn. The wildfires you are seeing now are the result of human interaction. Once you build a road across the jungle, when you have side roads, actually, when the farmers come, or first the loggers come, they take out the precious timber, when you set on fire areas, when finally you start to grow soybeans, and in the end you have cattle ranges, and after 20 years the ecosystem is dead, more or less. So what may happen is that you have this transformation from a mature rainforest, which is storing a lot of carbon, to a savanna, and finally can turn into a desert, because the Amazon rainforest is sort of recycling most of the water. And if you turn it into a savanna, this water recycling stops. And then the entire climate of South America would change, actually. So it would rather look like the Mediterranean, where the forests were cut down 1,000 years ago, actually, and where you don't have any vital forests anymore. And this, of course, will even influence the global climate. So these tipping points are extremely important, and as has been mentioned before, so I was ridiculed really when I introduced this notion that you have non-linear disruptive change in the system. But now this is actually the basis for defining what is dangerous climate change and why should we stop global warming between 1.5 and 2 degrees. So this is covered. And this is actually the master chart here. So we published this a few years ago, actually in 2016, here in Nature Climate Change. And this is, in a way, the map every politician should have in mind. Because what you see here is we're going back 20,000 years before the Common Era here. This was when the Earth was still in the last ice age. You see, global mean temperature was just 3 degrees lower than pre-industrial. Only 3 degrees. And it meant that the big ice sheets advanced actually into Europe, for example. When you see about 11,000 years ago, we emerged from the Ice Age. This was the absolutely stable period where human civilization was born. Homo sapiens was around for 300,000 years already. But only over the last 10,000 years we were able to develop agriculture, for example. Because you need an absolutely stable climate for that. And now see what are the prospects for the future. If everything goes well, when you could stop global warming at about 1.5 degrees. By the way, a global warming of 1 degree will persist for thousands of years. You cannot undo that. But at least we could peak and keep this temperature curve flat. But currently we are on this course, actually. This is business as usual. So that brings us, if you look around, to 8 degrees warming by the year 2500. I mean, it's a completely different world. So it is like your internal body temperature would be raised by 8 degrees from 37 to, you can calculate that, 45. So this would mean immediate exodus. But this is precisely what we risk the planet will experience. And now you can go back and see, this is the Paris Agreement range, you know, between 1.5 and 2 degrees. Somewhere in that range we have to stop global warming, because otherwise these are the error bars for the various tipping elements. So coral reefs, tropical reefs will be lost at between 1.5 and 2 degrees, including the coral reefs you have here around the southern coast of Taiwan. Great Barrier Reef will die. Greenland ice sheet, we don't know yet. West Antarctic ice sheet, we know we have crossed several tipping points already. So 2 meters of global sea level are already in the system, and it can't be undone, actually. But beyond the Paris range, you see here Amazon rainforest, major changes in the thermaline circulation, and finally the East Antarctic ice sheet would melt down. So this is the risk map, which would be actually the reference point for any policy, any energy and climate policy in any country of the world. Who is aware of that? So I've spoken to the German Chancellor several times. She knows that map. She's a theoretical physicist by training, which is very unusual. I think she's the only sitting president or prime minister in the world who understands that. Probably. I cannot judge on Taiwan, of course. But otherwise, this is the map humanity needs to steer us into the future. But very few people know about it. Any comments? Okay. So, in order to depress you a little bit more, we published a paper last year, and actually it's probably the most important paper I was ever involved, actually. It was about called Trajectories of the Earth System in the Anthropocene. And what we discussed there is more or less the interactions between the various tipping elements. For example, when you lose the Arctic summer sea ice, it means that you have an impact on the jet stream, and the jet stream again is creating these heat waves in the Arctic and has an impact on the permafrost. So we identified more or less 14 different cascades of disruptive events which accelerate global warming. Yeah? And this is a very important thing, really, because it means our assumption, the Paris Agreement, we calculated a so-called carbon budget, how much emissions are still allowed in order to push the Earth to 2 degrees warming, and when we stop. But this is the illusion that we can safely park the planet at 2 degrees. It may just spin out of control. It may not just sit at 2 degrees. It may just, by self-amplifying forces, move into a warmer era called a hothouse Earth, and that's what we discussed. And this is now for the geologists here. So Dr. Chen, for example, should be interested in that. If you go back deep in the history of the Earth, so 60 million years ago into the Eocene, for example, here you have the Pliocene, the Miocene, and so on. This is the expectation with business as usual. And you see, when you go back in time, it would mean, if we stay on the business as usual course, we would go back in time about 60 million years ago. So we would push in geological space the system back 60 million years. But we would achieve that in a few centuries only. So you see, humanity has become a geological force on Earth. Should we really do this geological experiment? I mean, the risk is so high. So I should show you also how the scientific assessment has become more and more dramatic, actually. This has not been published yet, for example, so it is a world first, what I'm showing you. You know, in the third assessment report, which later won the Peace Nobel Prize, we introduced this idea, reasons for concern. So you look at unique ecosystems, for example, and ask at what type of warming you start to be concerned. So if you have temperature, if you are in the current temperature range, so 1 degree warming, you enter already a danger zone, and this was portrayed by the yellow color, and when it turns red, and finally deep red, when you are very concerned. And you see now the evolution in our assessment, the best possible assessment over the years. So this was a paper published after the fourth assessment report. Here's the fifth assessment report in 2014, and now the special report on 1.5 degrees. And you see that the red color is coming down. We even introduced a new color in 2014, purple. So clearly you see evolution, that even at small global warming amplitudes, you have reason for concern. And this is on the tipping points here, you see. Third assessment report, we thought the dramatic nonlinear effects happen around 6 degrees. Okay, at 3 degrees you have to be concerned already a little bit. But see what is now in the special report. So here, after 1 degree warming, we enter the danger zone, and between 2 and 3 degrees we are certain that some dramatic things happen. So this is a really spectacular evolution in our scientific assessment. And in 5 years from now, with the next assessment report, which is due in 2021, probably the red color will have come down even more. So this means, and this is a sneak preview, we discussed it also with colleagues, the latest global climate model estimates that estimate that the so-called climate sensitivity, it's a thought experiment. Overnight, you would double CO2 in the atmosphere from 280 to 560. What would be the temperature response of the Earth? And in all the assessments report, we always came up with the range between 1.5 and 4.5 degrees. But currently, many models point to the fact that the climate sensitivity might rather be between 2.8 and 5.8 degrees. That is, the best estimate is about 4 degrees. And that would be, yeah, a devastating consequence, really. Yeah? And it has to do with many things, but probably with the cloud feedbacks, because there's an interesting paper. It is still being debated, of course, by Tapio Schneider here. Was published in Nature Geosciences just this year. And it simply says that if you increase CO2 concentrations in the atmosphere due to very subtle radiative forces effects, then over the subtropical oceans, the stratocumulus stacks will just break up. So you will have a situation like this. And when there would be a jump in global mean temperature of 8 degrees, just according to that effect. Now, we all hope that Tapio Schneider and his colleagues are wrong, actually. Yeah? So this will not happen. But at least it is something where you have a credible scientific mechanism. So if you include that, you have to be very worried. So I did this just recently. It's unpublished work, because I don't know how the debate is here in Asia, but in Europe and in the United States, people start to talk about climate emergency. And even some parliaments have declared officially climate emergency. So British Parliament, as long as it still exists, you know, we will not have the UK in 10 years from now. Maybe Scotland will split off and so on, but that's a political thing. We don't need to debate here. France has done this, Ireland and so on. So many municipalities have... Now, what is a climate emergency? And I tried to come up with a very simple explanation for that. So on the one hand, what insurance companies define is risk is damage of an event multiplied by the probability of that event. So it can be a typhoon, it can be an earthquake, whatever. What is at stake? So that's the potential damage times the probability. And here you see if probability is 1, it means the event is absolutely certain. Now, urgency, so air controllers, for example, is the reaction time you need in order to avoid a collision of planes, for example, divided by the intervention time left. So if this ratio approaches 1, you have lost control, clearly. Yeah? And you can illustrate it with the Titanic, for example. Once you see that you are on a collision course with an iceberg, how long does it take you to turn the ship around? And actually, it is reported that the captain of the Titanic waited for 30 seconds before he reacted. And this was about the time when you lost control, actually. Now, in our case, it means complete decarbonization of the planet. How long does it take? At least 20 years. But there are only 30 years left, actually. Yeah? And so you see, if you do the calculation here, we have almost certainty that we will reach 4 degrees warming by 2100 unless we intervene. And now you can argue about the damage. Economists would say, well, will only cost us 100 trillion US dollars if we have 4 degrees warming. I would argue it would mean the loss of our civilization. That means this number would be infinity in every line of argumentation. The probability is currently at 1/10, so 10%. The reaction time is 20 years. The intervention time left is 30 years. So, and if you do the calculation, you end up with at least 6 trillion damage, but it could be infinity. if there is an emergency at all on this planet, it is now, clearly. Yeah? So even if you do the simple numbers. So who became extremely interested, and I will sort of come to a conclusion very soon, is the National Security Advisors. So there's the famous Munich Security Conference. So for the first time, there was a plenary session on climate change. So you had all the generals sitting there, and they argued, of course, about the Crimean sort of crisis that Russia has sort of taken control of the Crimea again. And I showed them now what will happen if all the ice will melt. And you see, most of the Crimean problem has disappeared. By the way, also, the Brexit problem has disappeared, at least 50% of it, and so on. But and this is what would happen to Florida with the Greenland and the western East Antarctic ice sheet melting down. There will be no Florida anymore. But look at Southeast Asia. This is the most dramatic of all. If sea level rises, and in my physical intuition, we will at the very least have 6 meters sea level rise in the future. But this would be 70 meters sea level rise. Pick any major city. Let me see whether I can find Taiwan here. Okay. So, Hong Kong, yeah, of course, you can pick any major capital in Manila, Kuala Lumpur, Singapore, Ho Chi Minh City, Bangkok, Rangoon, whatever, Dhaka. I mean, they will all disappear, really. Can you relocate all these capitals, like Jakarta is supposed to be done? Let's see what will happen, actually. So this is a completely redrawing of the map of all our coastlines, really. Yeah? And of course, this would mean migration and so on. So let me go to the question, what can we do about it? Huh? And here Germany actually is, if you like, the canary in the coal mine, because Germany, after the Fukushima accident, decided to phase out nuclear by the year 2022. And actually, I was chair of an advisory council on global change for the German government. We issued this report in 2011, which is called the Social Contract for Sustainability about the Great Transformation. And now look what Germany has achieved over the last years. It was mentioned already by Sabrina before. So this is our energy mix in 1990. So you see nuclear, about 30% at the peak. You have lignite coal, you have hard coal, natural gas, and this was the contribution by renewables to our gross power generation, 3.6%. And I recall very well what Chancellor Merkel said when she came into office as environment minister. She said, renewables will never climb beyond 4%. So she went public with that statement because somebody has written down for her that. And now you see what happened to renewables until the year 2010. And this is the situation now. And as has been said by Sabrina, we are currently in the first half of this year around 45 to 50% contribution. So this is what we call as physicists the crossover. It's a phase transition that is happening, and now we will go up clearly to 100% by the year 2050. Now, phasing out coal at the same time is, of course, not easy. So this was the German Coal Commission, a civil society commission, so including a number of scientists, so including myself, Dr. Wersborn, who actually, I was teaching quantum mechanics a long time ago, and I met him again. He's now head of a Fraunhofer Institute. And we came up with his phase-out plan, exit of coal-fired power station by the year 2038. And this was really a dramatic thing, and probably my most important contribution to the climate and energy debate I ever made, because in the end, we scientists were the adjudicators. You had the trade unions, you had the industry associations, you had the environmental groups, but in the end, people referred to the scientific evidence. So we had to decide whether we make or break the compromise. And we decided we go for this compromise. This is far too late in my view. We should phase out coal already by the year 2030. But because of the investment dynamics, once you have a sunset clause, I'm sure phasing out of coal will happen much earlier, actually. The market will just force it to be closed down. And so you can look at the global scale, of course, about it. Maybe for your information again, these are the cost curves, by the way, here in logarithmic terms, here on the vertical axis. So you look at the cost development for the various sources of energy, and you see here this is the coal price for electricity generation. So it goes up and down, but it's more or less on the same level. When you see solar dramatically going down, same could be said for wind energy. The only energy cost which is rising per unit is nuclear. So nuclear is in no way an economic alternative. And since you are determined to phase it out, that's a very wise decision for Taiwan, actually. So finally, if we want to solve the climate problem, we more or less have to follow what we call a carbon law. That means we have to cut in half global emissions every decade. Not by 2050, every decade from now. That's the only way to achieve that target. And I skip this. Now comes the really important second message. Because we assume that we can reach the Paris Agreement goals, so stopping global warming somewhere between 1.5 and 2 degrees, if we deliver this carbon law, so halving emissions globally every decade, but only if the biosphere carbon sinks still do the service we are delivering to us, because about 60 to 70% of the CO2 emissions are sucked up by the oceans and by the biosphere. Without that, without this free service by the ecosystems, global warming would be already at 3 or 4 degrees. So what are we doing? We are killing our best friends. Instead of strengthening the biospheric sinks, we are killing them, the Amazon rainforest and so on. So you see, we only have a chance, actually, if we stop global deforestation. So any climate strategy that helps us to stop global warming has to be two-pronged. It has to deliver rapid decarbonization. That means disruptive climate innovation all over the world. And I'm absolutely convinced that Taiwan can contribute to that. But at the same time, we do not have to cut down forests. We have to reforest degraded areas. Only if we do this dual strategy, we have a chance. And I give you a concrete example what could be done. And this is something like an industrial revolution. Instead of building future constructions, houses, skyscrapers from steel and concrete, if you walk around Taipei, of course, you do not see many wooden houses. But going back to wood construction, actually, as we did in our calculation, this is my final slide, more or less. You see, this is the carbon budget we have still left. It's about, at best, 500 gigatons of CO2 equivalent. The budget between 2017 here and 2050. If we would do all the construction which is in the planning right now, in particular in Asia, based on minerals, that means in particular concrete, and you need a lot of cement, and you need a lot of sand for it. And we're actually running out of sand globally. Yeah, it's a big problem. when you would eat up at least 2/3 of the carbon budget left. While if you would switch to wood construction, just to give you a concrete example, we would reduce this consumption to almost 1/4 only. Yeah? So we could actually build ourselves out of the carbon crisis if we would switch to wood construction in the future. And now it sounds old-fashioned, but you can now treat wood in a way that it is at least as fire-safe as concrete. You can make it elastic, cross-laminated timber, for example. You even can make it translucent. So wood is the construction material of the future. And this is a message you probably did not expect from me, but it is one of the disruptive new ideas we need in order to save the world. So thank you very much.
Thank you very much. It's about time, but we can take one question if you do have. I guess you have too many to ask right now. But anyway, we have, one, please.
Thank you for your talk, but for your last suggestion, the wood for construction. When you look at Bahamas storm, all the building seems to be wooden construct, and that got all destroyed. If we have it in Taiwan, we have the same situation. How are you going to deal with this dilemma, the safety as well as the decarbonization?
Yeah. No, of course you need to have, in a way, a high-tech version of wood construction. No? So as I said, you can treat, there is an entire research center at the Technical University in Munich where we look at the properties, how you can make wooden construction, hurricane-proof, for example. So how to increase the elasticity. In the Bahamas, I mean, or wherever you look, Typhoon Haiyan in the Philippines and so on, of course the slums were destroyed completely. But you know, where you just take a few timber pieces and you nail them down in a ramshackle way, of course. But this is blown away by the storm is, of course, obvious and no surprise at all. Given that, of course, a simple concrete house is more stable, but you could actually come up, and that is precisely the innovation we need, new design, new architecture, new materials. If you would use cross-laminated timber, which is very stable, for example, and you might mix it with advanced material like carbon fiber, for example, then you can make it actually much more sort of robust than any concrete construction. It's an exciting field of research and innovation. And by the way, you can even make it fireproof. So 9/11, everybody has that in mind when the Twin Towers finally collapsed. It turned out that it was precisely because concrete was set on fire because of the impact. And you can now treat wood in a way that it would have an even higher point where it starts to burn, actually. So these are the obvious. I mean, when I first presented the idea in UK, people said, well, there was the Great Fire of London in 1666, and since that we haven't changed the building codes. But today, in the 21st century, we can treat wood in a way that will serve almost anything. It has a tremendous heat capacity. So, for example, if you want to avoid heavy air conditioning, if you use wood, I mean, you have much better conditions indoors when you have, if you just take concrete and when you have heavy air conditioning system. So I think many innovations will come along the way. And let's not forget, nature and evolution took 500 million years to come up with the optimal material for trees, and that's wood.
Okay, thank you.